Well, our last speaker for this late morning session is Donald Gantz. He is a professor in applied information technology, like Brad, also at George Mason University. The title of his presentation is On Parametric Models for Pairwise Comparisons with Applications to the Estimation of Random Match Probabilities.
Thank you, Bill. I'd like to acknowledge my co-author, John Miller, who's in the back of the audience, and my other co-author, Chris Saunders, who's watching streaming video back in Virginia. It's a great honor for us to be able to present at this symposium. We're very thankful. And I'm thankful that some of you are still around for another dose of statistics. I told them to lock the doors. Fortunately, it wasn't necessary. I'm going to steal from Joanne Biscaglia from the other day and take a poll by clapping hands. Those of you that are not really into statistics, clap your hands. And now the sounds of silence. Those that are into statistics, clap your hands. Not as silent as I expected. I'm going to be sensitive in the presentation. I think we have an important message for you. We're talking about random match probabilities, pairwise comparisons, and they certainly live in forensics. But I am a statistician, so some of my slides will have formulas on them. You'll notice that a lot of those slides have grayed out text in the background. That's stuff that I don't have time or sensitivity to talk about, and some sensitivity to the audience. The things I'll talk about will be in the brighter type. A frequent problem or a typical problem in forensics is the determination of whether two samples came from the same source. And that can be formalized by having a similarity score, and as Brad talked about earlier, a cutoff or threshold, where if the similarity scores exceed that threshold, then a decision's triggered, and correctly or incorrectly, you say that the two samples came from the same source. We're assuming in our model that we have a population of distinct objects. So if two of those objects are judged by a similarity score to be from the same source, that's a random match. And our focus is the probability of a random match. And that's when two randomly sampled distinct objects are erroneously judged to be from the same source. And we're going to present to you a statistically valid method for accounting for the what we'll call the correlation among pairwise similarity scores for pairwise samples, and coming up with a statistically valid upper confidence bound for the random match probability based on a sample. And that'll be a sample. We'll introduce the symbol little n to stand for the sample size of distinct objects from that population. And we're going to look at all pairs of those objects and apply a similarity score to get a pairwise comparison. And the symbol we use for it is the S with the subscripts I and J to identify the two objects. There's certainly a lot more pairwise comparisons than there are samples, and we use the symbol big N to stand for that number of pairwise comparisons. Now, the key statistical problem associated with pairwise comparisons is the correlation structure between similarity variables, or similarity measures. If I compare S12 to S12, they're the same objects, and the scores are certainly correlated, so we have correlation 1. If I compare S12 to S23, we have one sample, one object in common, and that gives us some positive correlation. If I compare S12 to S34, then they're totally different samples, and we have uncorrelated similarity measures, and that's correlation 0. An important quantity to us is a population parameter called theta. And I'll reference Steve Morgan from his statistical workshop on Monday, saying that statisticians like me sometimes have a fantasy world. There are these things out there that you can't put your hands on. They exist. We use them in our formulas. Theta is one of them. It's the average of similarity measures that I would get by comparing all pairs of objects in that population, all pairs of those distinct objects in the population. Obviously, I can't do it. I can't know what theta is. We'll estimate theta by looking at the similarity scores for all pairwise comparisons in our sample. And we're going to get a accurate assessment of the accuracy of that sample mean as part of our derivation of the upper bound for the random match probability. Issues of practice. Some researchers totally ignore the correlation structure in the similarity measures, and they treat the similarity measures for all pairwise comparisons as being independent, which makes the statistical inference incorrect. Some other researchers, they realize there's a problem, they get too conservative. They only look at those similarity scores from pairwise comparisons where there's no samples in common, like S12, S34, etc. Well, then they only have little n over 2 similarity scores to look at. They've thrown away the information from a lot of the pairwise comparisons that might have statistical power. Our method will use all similarity scores from all pairwise comparisons, account for the correlation structure, and give you a statistically valid upper confidence bound for the random match probability. Choked on that one. Our model. Our model looks at the similarity score comparing two objects I and j as being the sum of that parameter theta, a random quantity ai from object I, a random quantity aj from object j, and an error term. And we'll use that model as we develop the bound for the random match probability. Here's our model in matrix terms. Notice the suppressed gray in the background. Details that those people have a stomach for can look at later. The new notation introduced here is the vector y, which is our similarity scores. The vector a, which goes back to those random numbers that correspond to the samples, ai, aj, etc. And then a pairing design matrix P. And in 2 slides, you'll see a specific example of P. The model I just showed you, a statistician would say, oh, that's a multivariate statistical model for the similarity vector y. Well, immediately then we have a mean and an expected value. The reason I've shown you this slide is we have a 3-parameter model. You've heard of one of them, that's theta. The other 2 parameters come out from this covariance matrix for the multivariate model. And you see sigma e squared. That's the variance of each one of those error terms that you saw in the definition of the similarity score. And sigma squared a, that's the variance of each one of those a sub i's or a sub j's that you saw in the similarity score. So they're the 3 parameters. We'll estimate those parameters. We'll use the estimates when we get the upper bound for the random match probability. Now here's our example of a specific P and data vector for a sample of size 8. So data vector has 28 dimensions because that's how many pairwise comparisons you can get from 8 objects. The symbols, if you can read them in the data vector, are the similarity scores in lexicographic order, alphabetic order of the subscripts. So we have S12, S13, etc. Now, if we look at the 4th entry there, it's S15. That's the similarity score to compare objects 1 and 5. And if you look at the corresponding 4th row of the matrix P, it has 2 1s in the 1st place and the 5th place because they're the objects being compared. Each column will have exactly 7 1s, the rest zeros, because every object is compared to the other 7 objects. And mathematically, the structure of that design matrix is very important to our procedure, but it's, again, straightforward logic. Now here's a correlation matrix for that similarity data vector. It's 28 by 28, and it gives us what we call correlation coefficients. Well, if I'm comparing S12 to S12, we said before correlation would be 1, so you have 1s along the diagonal. If I'm comparing S12 to S23, the correlation is R. Now I got a formula for R at the top, and that's basically, it's the variance due to that sample in common, S12, S23, sample 2 in common, relative to the variance of the whole similarity score. So it's an indication really of how much influence that commonality has in the correlation. This table, or this matrix, has 12 R's in every row, and about 43% of the matrix entries are R's. That may be misleading because For larger n, for instance, n equal 100, there's only 4% of the matrix are R's. But no matter what number R is, or how many of them are in the correlation matrix, that correlation structure needs to be accounted for valid statistical inference. My colleague Chris Saunders, who's watching us on streaming video, hi Chris, he forced us to include this slide. It's a message to the statisticians. We have by our model, a normal structure on the A's and the E's in our model. And because of that normal structure, we get a log likelihood function. And then the bottom line of what you see there in the graph, or in the slide, are 3 sufficient statistics. And that's the key statistical information. The sufficient statistics are Y bar, SSA, a sum of squares due to the pairing, and SSE, a sum of squares due to error. The lambdas are the 3 unique eigenvalues of that correlation matrix we mentioned. The message to the statisticians, or whoever does this, is any statistical analysis, frequentist or the infamous Bayesian, need to acknowledge or be based on those 3 sufficient statistics. Why do I show you this slide? More equations. The 3 parameters that I mentioned before get an analysis of variance type estimates based on the data. We see that the estimate for theta is simply the average of the similarity scores, Y bar. The other parameters are estimated, as I say, by analysis of variance types estimates by taking those sums of squares I just mentioned. Now, down the bottom of that slide, in somewhat smaller print, I mentioned that we could combine the sums of squares for pairing, sum squares for error, and I call that SST. And if we divide that by the degrees of freedom, we get just the sample variance of the similarity scores. It's always, to statisticians, a useful measure, but it's a bad measure to use in the wrong place. And ignoring the correlation structure due to pairwise comparisons pretty much amounts to using that MST in the wrong place. Getting towards the end of the formulas, I introduced these to show you how bad that can be. The first formula you see is for the variance of the similarity scores in terms of the 2 of the parameters of the model. And the next is the variance of Y bar, the average of the similarity scores, again, in terms of the parameters of the model. So right away you think, oh, well, we have estimates in the previous slide of those parameters of the model. They can give us estimates of these things. The expected value of that sample variance, the formula is given to you there, is very close to the expected value to the variance of the similarity score. And that's good. But the expected value of the sample variance divided by cap n is very different from the variance for Y bar. And that's bad if you happen to use that as a substitute for Y bar. And people who ignore the correlation structure, that's effectively what they do. Now, endgame, 3 slides. We tell you how we get the upper bound for the random match probability. We said the random match probability is the probability that that similarity score exceeds some fixed cutoff tau, and that's it in symbols. To make things more simple, I represent the random match probability by pi. Again, Steve Morgan the other day said statisticians have a fetish for Greek numbers. True. In the upper left, you see pi less than b. That's b is an upper bound for the random match probability. Then a bunch of suppressed stuff, and on the right, you see a symbol gamma that substitutes for a certain quantity being greater than L. And that's a reversible relationship. If I start with L is less than gamma, then I can find AB, which is greater than pi. And that's a set of relationships that we use to bound the random match probability once we find L. Well, let me read the middle statement. If we could get a confidence bound with a confidence coefficient equivalently coverage probability, 1 minus alpha, by finding a random quantity L that meets that requirement of probability. Probability gamma exceeds L is 1 minus alpha. And then we're going to address how do you get L. A hypothetical. This hypothetical is going to be my basis for telling you how things can go wrong if you don't acknowledge the correlation structure. The hypothetical says, let's assume we know sigma E and sigma A. That's two of the three parameters. We don't know theta, but we estimate it by y bar, as we said earlier. Then we exploit that y bar is follows a normal distribution. That's from standard normal theory. And we get the probability statement you see there. The probability of an expression is equal to 1 minus alpha. And then a but, and more mathematical equivalences. That statement that's inside the probability parentheses is equivalent to blah, 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 gamma being greater than L. But we actually have a formula for L there. It's suppressed, it's in background gray. I'm not going to go through the details. But we've worked it out that, okay, now we have a valid formula for L. The only unknown in that formula is y bar. We said it's a random quantity L. Well, it depends on the data. We get the similarity measures, we get the similarity vector, we take the average, y bar, we get L. And we use the logic on the previous slide. We go back and we get the bound for the random match probability, and it has exactly the right nominal confidence level, coverage probability, 0.95 if alpha equals 0.05. But what if you don't plug in the right thing for sigma y bar in that formula for L? What if you plugged in that sample variance divided by cap n? Well, this is a set of results. The table that you see at the bottom is a table of coverage probabilities, confidence levels. And the nominal confidence level is 0.95. Notice, first of all, in that table, all those numbers are way far away from 0.95. Some of them are closer to 0.5. The structure of the table is for random match probability 1 in a million. Story is the same for any random match probability. I've introduced a symbol rho. Rho is the ratio of the variance due to the correlation, having that sample in common, to the variance due to error. And then we have a column for rho equal to 0.1 up to 10. When rho equals 0.1, that number r I told you about earlier would equal 0.08, so a little bit of correlation. When rho equals 10, the correlation is 0.48, which is a lot of correlation. And you notice as we go from left to right in the table, the coverage probabilities get worse. As we go down the table, we're going to bigger sample sizes. We start at n equals 10, we go to n equals 1,000. Now, usually in statistics, when the sample sizes get bigger, things get better. But notice what happens here. As the sample sizes get bigger, as we go to the bottom, things get worse. And the coverage probability actually approaches a half. So it's a terrible blunder. You'd be giving misleading information if you ignore the correlation structure in the pairwise. And I've got 3 minutes, which is plenty of time. Now, we want to do it right. Well, actually, when we first said, okay, let's do it right, let's plug in those estimates we have for our parameters back to that formula L, the proper estimates, and we'll do it right. No, it wasn't right. Oh, why? Well, there was a complication in the formula for L. It has a ratio of random variables, and you can't just do plug-in there. And we called on our old friend Feiler's theorem, something that if you've had regression analysis may have been pounded into you. And we got some good approximations, and this is a example where we've taken random match probability to equal 1 in 1,000 so that we can write the numbers in 4 decimal places. Story holds for any random match probability. Notice also we don't have the rho for n equals 10. That's because our application of Feiler's theorem doesn't really catch in at n equal 10, but for the other rows it's there. And also Feiler's theorem gives us a confidence interval rather than just an upper bound. So what we're giving you in each cell there is the coverage probability based on 1 million simulations per cell. And it's not perfect, it's not 0.95, but it's a real good approximation, and it beats the heck out of the previous table. And we do see the coverage probability holding up as rho gets bigger. We also see the coverage probability getting better, which statisticians like as the sample size gets bigger. So something to feel warm and fuzzy about. We can validly account for the correlation structure in pairwise comparisons and coming up with a statistically valid upper confidence bound for the random match probability. But there's a penalty. Notice the numbers in blue that are in that table. They're the upper bounds. In this, the true random match probability is 1 in 1,000. The worst case is the upper right-hand cell. We're 750% high than the true random match probability. Things get a lot better when there's less correlation and we have a bigger sample size. But you pay a penalty for being right. Your bound is a bit higher, but you're not lying to anybody. And contrary to belief, statisticians don't like to lie to people. Conclusions. Well, conclusion A I've already talked to. An advantage of this method is it can be used whenever your similarity score could be monotonically transformed to approximate normality. Another big advantage, if you're doing a experiment to find random match probability and you don't actually observe any random match probabilities, this model will still validly give you upper confidence bounds for the random match probability. This is a very active area of research for myself, my colleagues, John Miller, Chris Saunders. We're sharpening our results. We have a long research agenda that this is foundational for. We hope maybe we can talk to you again, keep you awake, won't have to lock the doors, and give you some updates. Thank you very much for letting me talk to you.
Thank you, Donald. Well, we've got a few minutes left for questions. If anybody in the audience has questions, don't shove and push each other out of the way to get to the microphones. Does anyone on the panel have questions for, you guys speak more of the same language. And I know from sitting here, it's difficult to formulate anything intelligent to ask, and I think everybody else is maybe feeling the same way. So, Dave, do you have something?
And no equations here, but I had a question for Ruth. Were the shoes that you used for the test, were they brand new shoes?
Yes.
So, just want to offer a comment that might explain what you're seeing. The idea would be we could hypothesize that there's one group of sites on new shoes that are easily filled and retained. So that would explain why there'd be a threshold number that would be from the very first site. And the remaining sites on the shoe would be ones that are much more readily exchanged. So the hypothesis would be when you went to that second site, right, you'd fill up the sites on the shoe that are easily removable, then you go to the third one and those get replaced. So might be something to test going forward.
Thank you. Yeah.
Oh, yes.
So, Don, I'm very interested in your match probabilities, and I've been dealing with doing statistics on spectra, and so typically an IR spectrum, the ones that Barry are dealing with, are 1,500, 2,000 dimensional. And I've been looking at distributions of correlation coefficients between spectra from samples that are matches with one another versus correlation coefficients between samples that are different. And the two distributions typically are not normal. In fact, they tend to be highly skewed and long-tailed in one direction or the other. And so the scores, a correlation coefficient, for example, would be the basis of the starting point for your sort of calculations, if I understand you correctly.
Right.
And you're saying that your method assumes that you can find a transformation that will normalize those scores? And so what sort
Yes, that's right.
What sort of transformations are appropriate for that situation? And will your method apply?
Well, you'd want to squeeze your data in and you want to take care of some of the skewness that you talked about. Now, I'm going to admit my shortcomings. My colleague, John Miller, that you're sitting with, is really the expert that can answer that.
I was going to ask him, but you had the microphone.
He was trying to set me up. John and I have worked together for 30 years and tons of problems. In fact, we've testified in court for 30 years in all kinds of statistical litigation, but not as forensics people. But he's the guy who teaches the courses that have all those transforms, and he can really help you. I'm a problem solver with data and numbers, and our combination of skills together with Chris Saunders is what allows us to do what we did today. But as far as those kinds of transformations, I won't BS you. You got to talk to John.
Yeah. Well, I have a lot of spectral data from fibers and other sources of trace evidence. I think it would be very interesting to combine some real data with your approach.
And
see how it behaves.
we'd love the opportunity to work with you on that. And that goes for really anybody in the audience. If you're interested in applying similarity scores to random match or to pairwise comparisons and random match probabilities, we'd love to talk to you, particularly if you have the real data. We are real problem solvers with data, and we have a large group of statisticians that are very complementary in their skills, and we lust after data.
Thanks very much.
Thanks. Thanks, Steve, for putting me on the spot.
Yes.
Hi, my question is for Barry Levine. I'm a PDQ user, and it would be great to be able to search spectra. Are you doing any work on being able to search a combination of spectra if we have multiple layers?
Right now, our work is focused on the clear coats. What you're suggesting might be future work. That would be my response. I was going to say the following. Once the search pre-filters cull it down, the two library searching algorithms that we propose to develop are one based on a cross-correlation function, because that takes into account shape and is also good for band shifting. And another one is based on a technique which was developed by Rob Lauder at the University of Kentucky in the early 80s, which had nothing to do with library searching, called BEAST. But it would be actually quite useful. But again, these sorts of sophisticated library searching methods will only work if you have a small number of samples, a couple hundred. Otherwise, if you were to use them for a full library, 25,000, 30,000 samples, you'd be there a long time. Well, in any case, that's the directions we're headed in for this project right now.
Great, thank you.
Okay, any other questions? Well, I'd like to thank the panel once again for, hopefully we'll have some additional insight into how we interpret our data and be able to express those intelligently. So thank you very much. And I guess we break for lunch.